Right. So as I mentioned, this is chapter 6, soil compaction. So this is a new chapter, and we have at least 3 lectures planned for this chapter. In soil compaction, what we're going to deal with is basically to improve the property of soils. And so far we know that soils are used for construction materials like earth stems, embankments for highways, or soil are also used as support for buildings and structures. And natural soils may not always give you the best properties in terms of compressibility, strength, or permeability. So when you're dealing with a site with less ideal soil, you have different options, of course. You can relocate your project site, you can adapt your foundation, or you can improve soil in situ. And the improved soil in situ option may be the most economical one for many projects. And that's what we're going to focus on in this chapter. And so I want to point out that there are many different techniques you can improve soil in situ. One of them is mechanical compaction. So that's what we're going to focus on in chapter 6. So when we say soil compaction, we're basically using mechanical force to improve soil properties. Okay. And in terms of our course objective, so remember this list of our course objectives, this compaction is one of the main course objectives. So basically in this chapter, we're going to understand the general principles of compaction, and also we're going to look at different compaction tests. So that's the, so how this relates to course objectives. In terms of the outline, today we're going to start on these general principles. So basically what soil compaction is and what are some of the fundamental principles governing soil compaction. And then we're going to look at compaction tests in the lab and also compaction in the field. So we're going to, as I mentioned, we're going to spend perhaps 3 lectures on this chapter. And for today, we're going to start on these general principles. The first for compaction, so what compaction is. So compaction basically, so we're trying to, what we're trying to achieve by compacting soil is to reduce the amount of voids in soil. If you look at this picture here, on the left-hand side, you have a loose soil that offers poor support. On the right-hand side, you have compacted soil, and it's more densified, so improve the load support. So we'll reduce the amount of voids in the soil by densifying. So we're basically pushing air out, reduce the amount of voids. And the result of compacting soil is reflected in the increase of unit weight. And sometimes people also use density to quantify this. So increase of unit weight or density. So that's what we're trying to achieve by compacting soil, reducing the amount of voids, and the result is reflected in the increase of unit weight or density. So next question is, why do we want a denser soil? So why do we compact soil to reduce the voids and increase its unit weight? And there are several reasons. The first one, with a denser soil, we have improved shear strength. So basically denser soil is stronger, has a higher shear strength. And also second reason here is to reduce compressibility. And reduced compressibility leads to less settlement. So you have less settlement. And the third reason for a denser soil is to decrease permeability. And the next one is to reduce shrink and swell potential. And finally, a denser soil also means you have less liquefaction potential, so reduce liquefaction potential. So those are some typical reasons why we want a denser soil. And to summarize all these, basically, we want materials with optimized properties for a project. So that's why we want to compact soil, and that's why we want to get a denser soil for a project. And so that's the purpose of soil compaction. And then in terms of fundamental principles, so I'm going to describe and learn the fundamental principles of soil compaction. And for that, So this slide shows Ralph Proctor, and back in 1930s, he published a series of papers based on his observed experimental behavior of soil compaction, basically how soil, unit weight of soil changes with moisture content. So he published his work termed Fundamental Principles of Soil Compaction. So we're going to look at this in more details. And that's basically what we're going to learn in this chapter is this relationship between moisture content and the unit weight of compacted soil. And that's attributed to Ralph Proctor back in the 1930s. And the first actually project, and this is a Bouquet Canyon Dam in Los Angeles, constructed in 1934. And this is actually the first earth dam in the United States that's basically constructed using the principle of soil compaction. So that's what Proctor described in his publication. So in this, basically, people use that compaction curve, which we'll describe in more detail, to guide the field compaction effort. And in terms of the lab procedure, so based on the relationship he observed, and Proctor actually designed a standardized test. That's what we term standard Proctor test. And this test, the objective of this test is to quantify for a given soil. So you want to quantify the moisture content and unit weight relationship. So in his study, Proctor observed that the unit weight of compacted soil is impacted by the moisture content. So he described that relationship using a curve shown on this slide. This is called the compaction curve. And I'll come back to this curve and describe all these axes and the observed behavior. But there are two pieces of information we're going to get from a compaction curve. The first one is this called maximum dry unit weight. And we use gamma D max. And the second piece of information is the moisture or the corresponding optimum moisture content we call WOPT. So that's the objective of a standard Proctor test, and basically to obtain this compaction curve and get these two numbers, two parameters. And as I mentioned, I'll come back to this in just a few minutes. And next, I want to describe a little bit in detail what this Proctor test looks like. So that's something you're going to practice in the lab. So in the Proctor test, on the right-hand side, this shows the standard Proctor test equipment. So you have a mold here. So that's where you're going to put compacted soil in. And this mold is attached to a base plate. So you have a base plate. At the bottom, and also an extension on top. Okay, so that's what the device looks like. And for standard Proctor test, you know the volume of this mold. This is a fixed volume mold. So you know the height, you know the diameter. So you can calculate the volume, which is 1/30 of a cubic foot. So that's a fixed volume mold. Okay. And then on the right-hand side, it's a hammer. So in a standard Proctor test, so what you do, basically, you mix soil with varying amounts of water. So you have different moisture content. And then you compact soil in 3 layers in the mold by a hammer. And this hammer is dropped from a fixed distance, fixed height, 12 inch. As I mentioned, you compact soil with different moisture content in layers. So you have, for standard Proctor test, you compact soil in 3 equal layers. And for each layers, you use a hammer to deliver 25 drops, 25 blows to compact the soil. Basically, compact soil in 3 equal layers, and for each layer, you use the hammer to deliver 25 blows. So that's a procedure of the standard Proctor test. And so this is a picture of the equipment. Something you're going to use when you conduct this test in the lab. And the in the standard Proctor test, for each test, the moisture unit weight of compaction, this gamma. So for each test, for each soil sample, you have a moisture unit weight. We call that gamma, is total weight over total volume. And in standard Proctor test, you know the total volume is volume of the mode. So that's a fixed number. And you also know the moisture content. So you can measure the moisture content of your soil sample. And from that, you can calculate the dry unit weight. So the dry unit weight, gamma D, is the moist unit weight over 1 plus water content. And if you're using percentage for water or moisture content, so let's say W, divide that by 100. Okay. So that's the dry unit weight. Okay. So basically for each test, you have a pair of gamma D and moisture content. So no moisture content. Okay. And you vary the moisture content, you compact the soil, you get another gamma D. Okay. So you repeat this process for soils with different moisture content, and the results are plotted in that compaction curve. Okay. So let's look at this compaction curve in more detail. Right-hand side, this picture is an example of a compaction curve. And for this compaction curve, on the horizontal axis, you have moisture content. And on the y-axis, you have that dry unit weight. Okay. So you may have 3, 4, 5 different soil specimens. So that's your data points. Let's say you have 6 tests. You performed the 6 tests, each one with a different moisture content. And you connect these points, you get your compaction curve. And if you look at the behavior of this dry unit weight versus moisture content on the compaction curve, notice there are 2 distinct stages. So the first stage is this initial increasing stage. So if I call this stage 1. So stage 1 is pretty clear. As you increase the moisture content, the dry unit weight of the compacted soil increases as well. Water content increases, the dry unit weight increases as well. Okay, so that's the first stage. The water content increases, dry unit weight increases. And the second stage is this decreasing stage here. So notice the dry unit weight decreases with water content. This is stage 2. Okay. So in stage 2, the water content, as the water content increases, the dry unit weight actually decreases. Okay. The reason for these 2 different distinct behavior for stage 1, when water content is relatively low, as you increase water content, water lubricates soil particles. That's why you see this increase of dry unit weight. So this lubricate effect allows soil to pack denser, to move closer to each other. In the second stage, as you further increase water content, water takes up void space that would have been occupied by soil particles. So that's why as you increase water content in stage 2, you'll see the the dry unit weight actually decreases. And this turning point here, right here. So this peak point on the compaction curve gives us that 2 important pieces of information. The first one is that dry unit weight max. So that's gamma D max, the maximum dry unit weight. And the second pieces of information, so this is gamma D max. Okay. And the second piece of information is the corresponding moisture content. So that's this point here. And that's water WOPT. Okay, that's optimum water content. Okay, so that's the compaction curve from standard Proctor test. Again, it gives you that moisture content versus dry unit weight relationship. And what you want from this curve are these two numbers basically, gamma D max and water moisture, or WOPT. And on this figure, I'm also showing this curve here. So I'm going to go over this one. Okay. If you look at this curve, there's also this line here. Okay. So this is called zero air void curve, zero air void line here. Okay. So this line here, ZAV curve. So this is basically a theoretical bound. It's an upper limit of a dry unit weight. Okay. So this is a theoretical maximum dry unit weight at a given moisture content that corresponds to degree saturation of 100%. So that's the theoretical maximum dry unit weight you can get for a given moisture content. But in reality, you're not going to get that gamma D theoretical max ZAV. So that's why I put a note here. If you look at the compaction curve, it always lies to the left of the ZAV curve, which means any point on the compaction curve, the dry unit weight is smaller than the theoretical maximum. So for a given, say, let's say for this curve, so gamma of 15%. From the compaction curve, you have the gamma D of that compacted soil, and it's always smaller than the theoretical bound from the zero air void line. So that's the theoretical bound. Okay. So this compaction curve always lies to the left. So I'm showing on this slide two phase diagrams. ZAV, as I mentioned, it's the unit weight corresponding to 100% degree saturation. So that's the one on the left-hand side. So the gamma D corresponding to S of 100% is gamma D ZAV. And generally your soil in the compaction test is going to be a moist soil. So that's a phase diagram on the right-hand side. So this gamma D ZAV, so it can be calculated using specific gravity. And water content, unit weight of water, and degree saturation, and water content. Okay. So we can express the unit weight of soil using these quantities. And for ZAV, gamma ZAV, so I want to show how you can use phase diagram to derive this relationship here. So this is a fully saturated soil, so we have solid and water. And to show the relationship of gamma DAV with these given quantities, I'm going to assume volume solids is 1. Okay. And then the weight of solids is simply GS gamma water. This is something we derived back in chapter 3, weight volume relationship. So that's the weight of solids. And then the weight of water is water content times weight of solids. And then the volume is weight over unit weight of water. So that's omega GS or WGS. Okay. So that's a completed phase diagram. And for this, so the only step I skipped is this one here. So WS. Okay. So it's gamma S VS, and gamma S is GS gamma W VS. So that's how I get that GS gamma W term. Okay, VS is 1. So once you have the completed phase diagram, then this gamma D ZAV is weight of solid over total volume. Okay. And this is weight of solid is GS gamma W over total volume is 1 plus WGS. So this is how you can get this gamma ZAD expression from the specific gravity, unit weight water, and this water content. And then for the moist case, so this is basically that gamma D moist. Again, I start with this Vs equals to 1. So Vs equals to 1, then Ws, this is GS gamma water. And then the weight of water is water content times GS gamma water. And volume water is basically weight of water divided by unit weight. This is water, air, and solid. And if we want to express gamma D for moist soil in terms of degree saturation and water content, so you need to find out this gamma, the volume of void. So volume of void, so one thing we haven't used is a definition of degree saturation. So degree saturation, okay. Volume water over volume of void. So for this VV, EW over S, okay. So you get an expression for VV as well. So this is water content, GS. Okay. That's the B water divided by S. So this VV is basically V water divided by degree saturation. Okay. So that's a complete phase diagram. Then we have this gamma D expression. Weight of solid over total volume. And weight of solids is, again, GS gamma water divided by total volume, which is 1 plus volume of the voids. So this is a text, if you look at your textbooks, both expressions are in your textbook. And here I'm just using the phase diagram to show you how you can derive these two relationships from basic definitions and phase diagram. Okay, so that's the gamma D ZAV, and that's basically how you obtain this curve right here. Oops, so this is the ZAV curve. Okay, so this gamma D ZAV. So you can use that expression to calculate gamma D ZAV. And just one more, if you, hold on, let me actually, so there's one more thing you can do here. So if you're given the void ratio E, you can also write gamma D in terms of the void ratio. So that's even easier. If you know the void ratio, the total volume is basically 1 plus the void ratio E. Okay, so then your gamma D is even easier to calculate. So that's total weight over total volume. Right. So that's the zero error void line. And this picture basically summarizes the standard Proctor test. If you look at this picture here, we have, this is the mold with fixed volume, and we have 3 layers, 1, 2, and 3. So we have these 3 layers, and we know the weight of the hammer is dropping from a fixed height, and then you use 25 drops per layer, 25 blows per layer to compact soil. Okay. So this summarizes this standard Proctor test. And what you get out of this, so you get the volume of the mold, which is basically the total volume of soil. You can measure the moist soil, the weight of the moist soil in the mold. And you can also measure the moisture content. Okay. So that's what you get, the data you get from a compaction test. For this example here, we have 1, 2, 3, 4, 5, 6. So basically you prepared 6 soil samples each with different moisture content, and compact these 6 soil samples. So you have this table here. Again, this is something you're going to do in the lab next week. So you're going to perform this test, and this is the data you're going to get from a compaction test. So that's standard Proctor test. And this Proctor test is later modified by the US Corps of Engineers during World War II to construct airfields. And the reason for this is that this modified Proctor test actually better reflects the modern compaction equipment and is better reflect the behavior of higher strength materials. So if you look at the comparison here, there are a few things that are different. In the modified Proctor test, the weight of the hammer is larger. So you use a hammer with 10 pounds. So the weight of the hammer is 10 pounds. The distance is 18 inches instead of 12. And then you're compacting soil in 5 layers instead of 3. Okay. So basically, all these lead to higher compaction energy. So in the modified Proctor test, you are putting more energy to compact soil. So increase the compaction effort or compaction energy. So we're putting more energy into soil in the modified Proctor test, which increases the measured gamma D max. Again, as I mentioned, this modified Proctor test better reflects the modern compaction equipment. So you put more energy basically using these modern equipment to compact soil. And this modified Proctor test better reflects that. And if you look at the behavior of that compaction curve, if this is a curve for the standard Proctor test. So this is a compaction curve for standard Proctor test. In the modified compaction test for the same soil, the curve is going to shift to the left and also shift upward as well. This is the modified. So that's how this increased energy affects the compaction curve. So you have higher dry unit weight, and also the optimal moisture content slightly decreases as the curve shifts to the left. So that's the Proctor test, standard and modified Proctor tests. The next thing I want to talk about is some factors that are affecting the compaction. And we have described that relationship between moisture content and dry unit weight. So of course, moisture content impact your compaction. And there are other factors that will impact compaction as well. And the first one is soil type. And on the right-hand side are some typical compaction curves for different types of soils. And the one we have seen so far is for silty clay. So for silty clay, you have this type of behavior, but if you have different types of soil or sandy silts, but if you look at this poorly graded sand, so notice the behavior is very different from, say, a silty clay or sandy silt. So soil types will affect the compaction. And the other factor that impact your compaction is this compaction energy or compaction effort. And so one example is that modified versus standard Proctor test. So in the modified test, you have more compaction energy, compaction effort. So that affects it. So this slide shows how this compaction curve moves as you increase the compaction energy. So basically, as compaction effort is increased, so if you look at these 4 different curves, so you have one basically layer with only 25 blows. So that gives the lowest compaction energy. And then if you increase, this is case number 1 with 20 blows per layer. And then case number 2, you have 25 blows per layer. So that energy is increased. Case number 3, 30 blows per layer. Case number 4, 50 blows per layer. So you have basically you're increasing the compaction energy, and the effect of this is shown on this slide. So the dry unit weight of compaction increases. So remember, the gamma D max is basically the gamma D corresponding to the peak point. So this gamma D max increases as a compaction effort increases. And then the optimum moisture content, which is the x-axis, basically decreases slightly. So see, you increase the compaction effort, it actually slightly decreases the optimum moisture content. Okay. So that's the effect of compaction energy. And finally, I want to briefly mention the effect of the compaction on soil structure. So this is something we discussed in chapter 4, soil structure and plasticity. And this compaction will impact the structure of soil. And for clays, if you're compacting dry of optimum moisture content, so if let me add it. Okay, so this is optimum moisture content. And dry of WOPT simply means you're compacting soil at water content smaller than WOPT. So this is the dry side. And this is the wet side. Okay. So same for the soil here. Okay. So this is WOPT. This is dry. This is wet. Okay. So if you're compacting soil at a moisture content smaller than the optimal moisture content, the structure of the clay is more flocculent. And if you're compacting soil on the wet side, meaning the moisture content is higher than the optimum moisture content, then you're going to get a more dispersed structure. Okay. And then if the moisture content is fixed, if you're compacting soil at a fixed moisture content, then higher compaction effort will yield a more dispersed structure. So that's how compaction changes soil structure, how compaction affects soil structure. And this table basically summarizes the behavior of compacted clay when you're compacting. So here I'm listing dry side. So the wet side, the behavior is opposite to this. So it shows basically how this compaction changes the structure, permeability, and the strength of clays. So, so basically for structure, if you're compacting soil on the dry side, particle arrangement is more random, and water deficit, you have more deficient. And if you're compacting soil, the structure is more sensitive. And then for permeability, if you're compacting clay on the dry side, the permeability is going to get more pervious, more permeable basically. And the permeability, the permanence of permeability change is reduced by soaking. In terms of the effect on undrained shear strength, on the dry side, we tend to get higher undrained shear strength. If soil is soaked, then the undrained shear strength will be higher if swelling is prevented. And the undrained shear strength will be lower if swelling is permitted. And the pore pressure at failure, if you compact soil on the dry side, is going to be lower. Okay. and the wet side behavior is basically opposite of what's shown here. Okay. So that's how compaction affects the general behavior of clays in terms of its structure, permeability, or undrained shear strength. Okay. All right. I think this is a good point to stop. So these are basically some general principles of soil compaction, and also the standard and modified Proctor Test. Next lecture, we're going to look at example on soil compaction. So I'm going to go over this example next lecture, and then I'm going to go over field compaction as well next time.